Today we're going to talk about the Intermediate Value Theorem. Let's first recap some ideas from before. For today's lesson, we'll let f be a complete ordered field, such as the real numbers. Given any two numbers a and b, where a is less than b, we'll define the closed interval from a to b as the set of those x such that x is greater than or equal to a, and x is less than or equal to b. Given a closed interval I, we'll say that a function lowercase f going from the interval I to the complete ordered field f is a function if each f of x is defined and unique whenever x is an element of the closed interval. Given a point P, we'll say that f is continuous at P if two things hold. One, f of P is defined and unique, which we'll denote as L, and two, for every positive epsilon, we can find the positive delta such that, in absolute value, f of x minus L is less than epsilon whenever, in absolute value, x minus p is less than delta. Otherwise, we'll say that f is discontinuous at p. We'll say that f is continuous on the closed interval I if f is continuous at p for every point p in the closed interval. Given such a closed interval I, let's say that f is a continuous function. Then, whenever we have a convergent sequence A, where x sub n converges to a point P, then f of xn converges to f of p. As a special case, let's consider what happens when our function f is either increasing or decreasing. First, let's take a subset S of our closed interval I. It is bounded, so both the supremum and the infimum exist. Let's assume that f is an increasing function. That is, f of x is less than f of y whenever x is less than y. Then f evaluated at the supremum of the set S is just the supremum of the set f of capital S. Next, let's assume that f is a decreasing function. That means f of x is greater than f of y whenever x is less than or equal to y. Then f evaluated at the supremum of capital S is the infimum of the set f of capital S. Today we're going to talk about some properties of continuous functions. In particular, we'd like to talk about three specific theorems. The first of our three is what's called the Intermediate Value Theorem. Let's assume that f is a continuous function on a closed interval I from a to b. Choose L to be any number in our closed ordered field that is between f of a and f of b. Then there exists a p such that f of p equals L. That is, f attains all of its intermediate values between f of a and f of b. The second of the three is the Boundedness Theorem. Again, say that f is a continuous function on our closed interval I. There exists a lowercase m and an uppercase m such that lowercase m is less than or equal to f of x is less than or equal to uppercase m for all x in our closed interval. That is, f is a bounded function. And the third of our results is what's called the Extreme Value Theorem. Again, say that f is a continuous function on our closed interval I. There exists a point c in our closed interval such that f of x is less than or equal to f of c for all x in the closed interval. That is, the function f attains its maximum on this closed interval I. And finally, there exists a point d such that f of x is greater than or equal to f of d for all x in our closed interval. That is, the function f attains its minimum on this closed interval I. Let's try to go over a few examples just to illustrate how this works. Let's consider the following graph. You'll see that the Intermediate Value Theorem simply says that this looks like a nice continuous string. If I pick any 2 points here on the string, then there will always be some L that will lie somewhere in between these 2 points. Also, if I fix any 2 points, then we see that we do have a bounded graph. It doesn't seem to run off to infinity. And also, the extreme parts of this graph, you can see here how we have a hump to the left that seems to be very high and a trough to the right that seems to be very low. those are high points and low points, those extreme values, are indeed points on the graph. But here's a non-example. You can see here how the intermediate value theorem fails. Here in the middle of the graph, we seem to have two disconnected parts. That is, we don't expect the function to take on all values in between. Second, clearly here in the middle of the graph, we have a graph that is not bounded. And third, we see that the graph does not even take on its extreme values. We see here in the middle how things run off to infinity, and there's no way that we can find a point in the graph that will run off to infinity in this way. Let's talk about the proofs of these three statements. I'd like to start with the proof of the intermediate value theorem. Recall that L is given, and we'd like to know that we can find a point P such that f of P equals L. So upon fixing our L, let's assume, without loss of generality, that f of A is less than f of B. There's a similar proof if f of A is greater than f of B. But assuming this, I'd like to consider the following set. This is the collection of points in the interval I such that f of x is less than or equal to L. Again, remember that L is given to us. Our S here is a non-empty bounded set. So we see that it must have a least upper bound. Let's denote P as this least upper bound. We're going to prove that f of P is our chosen L. We'll do this by showing that the difference f of P minus L is less than or equal to epsilon for every positive epsilon. Since our f is a continuous function, we can find the delta such that in absolute value, f of x minus f of p is less than epsilon whenever in absolute value, x minus p is less than delta. Unpacking what it means to be an absolute value and adding or subtracting if necessary, we now see that we have a couple of inequalities. Namely, f of x minus epsilon is less than f of p, which is less than f of x plus epsilon, whenever p minus delta is less than x is less than p plus delta. Here, we're going to break up our proof into two cases. The case where x is less than p, and the case where x is greater than p. First, let's say that x is less than or equal to p. Recall that x must be in S because p, recall, is the least upper bound for our set S. Since f of p must be the supremum of f of s, recall that we're dealing with a continuous function, this means that we can find an x sub epsilon such that, first of all, our x sub epsilon must be in S, so x sub epsilon must be less than p, and second, we are dealing here with a continuous function, so our x sub epsilon must be between p minus delta and p plus delta. But this x sub epsilon satisfies the property that f of x sub epsilon must be very, very close to f of p. That is, f of x sub epsilon plus epsilon is greater than or equal to f of p. On the other hand, x sub epsilon is an element of our set S, so f of x sub epsilon must be less than or equal to p. Now let's consider the case where perhaps x is greater than p. In this case, because p is our least upper bound for the set S, we see that this x cannot be an element of S. So in particular, f of x must be greater than L. Recall that S was chosen to be the collection of all x such that f of x is less than or equal to L. So if x is not in S, then f of x cannot be less than or equal to L. In this case, again, we're dealing with something that has to be in our region from before. X is between p minus delta and p plus delta. Then we see that x has to be between p and p plus delta. As mentioned, f of x is greater than L, so f of x minus epsilon must be greater than L minus epsilon. On the other hand, because we are dealing with the epsilon delta definition from above, then we actually see that f of x minus f of p must be less than epsilon, or in other words, f of x minus epsilon must be less than f of p. But now let's put both of these together. We see now that L minus epsilon must be less than f of p. This is the latter equation we just worked out. And this must be less than or equal to L plus epsilon. This is the first equation we worked out when x is less than or equal to p. So indeed, in absolute value, f of p minus L is less than epsilon for any given epsilon, showing that f of p must indeed be L. Now let's discuss the boundedness theorem. Recall that we have to find bounds lowercase m and uppercase m for our function f. Let's assume, by way of contradiction, that f is not bounded. Without loss of generality, let's say that there is no uppercase m such that f of x is less than uppercase m for all x in our closed interval I. If this is the case, then this means that we can actually find a sequence that increases without bound. That is, we can find x sub n in I such that f of xn is greater than n for each n being 0, 1, 2, just a natural number. But now our sequence of the x sub n's must be contained in I, so it is bounded. Hence, using the Bolzano-Weierstrass theorem, we can find a convergent subsequence. But now, this set B must be bounded because it is contained inside of the closed interval I, so we can take a look at its limit P. In fact, at the limit P, our function f must be defined and unique. But there's a problem here, because the way that we've chosen this, our f of xn is greater than n for each n, so this means that our f of p must be greater than every n. In particular, f of p cannot exist. This is a contradiction, so our function f must indeed be a bounded function. Finally, we'll show the extreme value theorem. First, let's recall some ideas from the boundedness theorem so we can set up what we'd like to do. We can find a set S as follows. Our function f must be bounded from the previous theorem, so let's consider the set of f of x, where x comes from the closed interval I. This set must be bounded, so let's denote lowercase n as the infimum, the greatest lower bound, of the set S, and let's denote capital M as the supremum, that is the least upper bound of the set S. We're going to show that there do exist points in the closed interval I, namely C and D, that take on these two extreme values. That is, there should exist a C such that f of C is capital M, and there should exist a D such that f of D is lowercase m. For each natural number n, let's find numbers c and d in our closed interval such that f of cn is very close to this least upper bound, and f of dn is very close to our greatest lower bound. In other words, f of cn plus 1/2 to the n should be greater than or equal to m, and f of d sub n minus 1/2 to the n should be less than or equal to m. This means that we have two sequences that converge to our least upper bound, capital M, and greatest lower bound, lowercase m. But now, looking at the c sub n's and d sub n's, we see that they are bounded because they are contained in our closed interval I. So according to the Bolzano-Weierstrass theorem, we can find convergent subsequences. However, if we have convergent subsequences, then they must converge to the same limit. So our f of c has to be the same as our f of cn's, which from the way that we constructed everything has to be m. So the limit here, that is coming from our convergent subsequences, does indeed give us the c's and d's that we wanted in the first place. Thanks very much for watching.